Okay. Okay, please go.
Cool. Well, thanks, Lev. Thanks again for attending and setting this up. It's really fun to put these out there, and I like watching them on YouTube. So it's good content. So today we're kind of doing a follow-up on a previous seminar we did about 6 weeks ago, and so this is basically part 2 of forecasting, building forecasting models using tree-based ensembles. So I'm Brett Efaw. I'm a data scientist at Idaho Power, and I've been working with Lev for a bit now, maybe 6 months or so, setting up our Azure environment and doing some general data science, machine learning type stuff. And so one of our use cases is forecasting call volume from our call center. And so we've been playing around with lots of techniques or approaches to building high interval or high frequency time series forecasting models. So today I'm going to basically pick up where we more or less left off a couple weeks ago. There's a link here to the past seminar where we talked about different ways to approach time series and maybe some pros and cons to the different approaches. And ultimately we compared this tree-based ensemble using XGBoost or gradient boosting to an Auto-ARIMA procedure on a pretty simple simulated data set, just to kind of get the mechanics ironed out. Today we're going to basically revisit this and kind of do the same thing, but use a more interesting simulated data set with a little bit more realistic trend and some holiday effects that we can kind of build in. And then also go over a data set I found on Kaggle of some daily website visits that has pretty similar characteristics to the data I've been working with. And then we'll also talk a little bit about updating that Auto-ARIMA procedure using what in econometrics they call exogenous regressors, basically external regressors. So this new simulated time series data set will have, again, multiple patterns, multiple seasonality going on. So like day of the week and day of the year patterns, but then also a nonlinear trend. This is probably more realistic than what we talked about last time, where we just had a straight line increasing trend throughout the entire time series. And so this basic process that we're kind of working with here is we're essentially building 2 different models. One is we're going to model the trend. And so how do we do that? We have to extract it and build a model to forecast it. And then we'll build a second model where that one is looking at the remainder of the first model, basically the detrended data. And that's where we'll use our tree-based algorithm like XGBoost or random forest. And then to make our final forecast, we're going to combine both predictions together. So first we'll start out with this simulated data set. And I did this, and Lev and I kind of wanted to do this so we could share all the notebooks. So this is the notebook that accompanies this, excuse me, and the Kaggle data set we'll make available so you can get your hands on this and play around. It's actually kind of fun to try different things and mess around with this a little bit. But this simulated data set will basically create, I think it's about 6 years of daily data. And obviously you can change that if you get your hands on it and mess around with it. But we'll have patterns for day of the week, day of the month, day of the year created into it. We also, on this one, created some calendar features or some holiday features from this calendar module from Pandas. And so we create a feature for the holiday, like a federal holiday, as well as the day before and after the holiday. But this could be anything in your time series data. Maybe you have special events, or the data you're working with, maybe there's sales. Or I saw one example of a special event was the Super Bowl. Just depending on the data you have, you might have interesting events. One of the couple of time series that I used, I built in special features basically for when we had certain COVID protocols going on in our call center that were affecting the call volume. And so that would be kind of another example of kind of one-off effects you could build into the time series modeling process. And then probably the most interesting thing from the last time we did was, instead of just putting in a straight line trend in the data, we wanted to create something that was a little bit more realistic, and it was kind of based on just randomly creating change points throughout the time series that would go up or down, and then accumulating those across the time series and then smoothing them out using a Savgol filter. And so those, you can see all that in the notebook if you look at it. And every time you rerun it, you'll obviously, if you set those random, unless you set a random number at the top that keeps it from changing, it'll change the data every time you run it. So on a particular run, this is the result I got. And so you kind of see a snapshot of the first few rows of data. So we've got the one row for every date. We've got a target variable, we call it Y, and it was actually just derived from a bunch of these, combined, adding all these things together. And then we've got some features for day of the week, day of the month, day of the year, all that kind of stuff. And then some random noise also thrown into there. And then the plot there is showing what that looks like. And so you can kind of see the, excuse me, periodicity throughout the course of the year. You can also see about halfway through, starting in 2019, we had a run of random up values that just kept happening. And so it kind of trended up. Before that, the trend was pretty flat. So a lot of times you get a time series data set and it's not just one single trend throughout the whole thing. It kind of changes throughout the course of the historical data that you have.
Oh, Brett, sorry. Can you return to the on this slide on the top when you have day of the week, day of the month? Can you please explain why there are not integers but some numbers?
Yeah, so these are the actual integer values, and then these right here are sine cosine transformations of those. So basically, the kind of sticking the range of those between -1 and 1 on a sine cosine scale. The reason I made these for the simulated data set is so that I could actually create this sinusoidal signal in the target. In a real data set, you could use like day of the week integers, day of the month as an integer, or you could use these trigonometric transformations as well. I've used both with like XGBoost, and it works just as well. Sometimes these are a little bit better if you have really smooth patterns in those in the time series. But one of the benefits of the tree-based algos is that they're pretty flexible and robust to different scaled inputs and inputs that may not be maybe correlated with each other. So these were here just so that I could create the signals in the time series, but in reality, you could use them as input features. So for our particular simulated data set, I'm just going to use the integer features plus the holiday features. So this kind of this approach of basically building two models, one to address the trend and then one to kind of take care of all the residuals of the trend. So the first part is, what do you do with the trend? And so the approach I took was to try to extract the trend from the data. And I used in stats models, TSA, there's a module called STL for seasonal trend lowest decomposition. And so that can extract the trend. And the main parameter there is how many time steps to include in that smoothing of the lowest. And so for daily data, if you have, say, 90 days or 91 days in the smoother trend, you would kind of favor kind of a shorter term trend of the data. Whereas if you put in like 365 or maybe 2 years, you might tend to favor a little bit longer term trend. And so this also would affect your forecast horizon. So if you're making relatively short forecasts into the future, maybe you'd favor smaller values on this trend decomposition, as opposed to if you're making longer forecasts into the forecast horizon, you might favor a little bit larger values, but that's just another parameter you can play with. So then once you extract the trend, you're going to use that to detrend the data so that you can feed that output to your tree-based model. but then you're also going to build some kind of model or do something with that extracted trend to forecast into the future. So to do that, I just used the Auto-ARIMA module from Stats Models TSA to build a fairly simple, just autoregressive model on the trend values. And so the parameter there would be how many lags do you use? And again, this kind of the number you pick depends probably on how far out in the future you're trying to forecast. So once you do those two things, you detrend the past values because you need those as basically your target for the secondary model. And then you forecast that trend model into the future, or your testing split if you're doing backcasting, so that you have those trends in the future. You could theoretically also kind of interject some subject matter expertise into this piece. Maybe you know something's going to happen in the future, like you're going to spend more on marketing or sales, so you think that it's going to impact, make the trend go higher, or you think it might go lower for whatever reason. You could theoretically kind of toggle the trend based on some other information that you might have. And for this one, I'm just plugging in whatever the model output. Just some other parameters to keep track of. We're using daily data, so the frequency is 7 for all of our stats models modules. And then for the evaluation of the models, I'm using 4 splits of train test for historical data with a test size of 365. So I'm making fairly long forecast horizon forecasts. And so here's a graph of the 4 splits. So those are the 4 rows that you see. And another parameter I left in there was to use as much historical data in the training data set that you have. And you can change that if you want, where basically you fix the amount of training data that you want each split to be allowed to see. And so, that's just kind of a personal preference thing. I usually tend to think that you're going to use as much historical values as you want to fit whatever model. So I just, each split uses all the way back to the beginning of the data set that we have. So in here, we've got the actual values. You can see those in red. And then that kind of, I guess, is orange or green line through the red is the fitted values for the trend using STL. And then the blue is using the AR model to forecast the trend into the future. And I'll just note that you can kind of see, at least for the first 3 splits, if you look at the first split and then the one right below it, you can kind of see where the trend or where the data was going. And you can kind of see between split 2 and 3, or because Python starts at 0, it's split 1 and 2. The split on the second row kind of says the trend is going flat, where in reality it ended up going a little bit higher. So we'll kind of keep track of that later on when we evaluate some of the accuracy. But generally speaking, we're just trying to cast the data out into the future without trying to explain too much of the cyclic patterns. So here's the detrended data. So this is the actuals subtracting out the fitted trend. And kind of the goal with this piece is to have a fairly straight output. And the whole reasoning behind this is because when you fit a tree-based ensemble, that model can't physically predict outside the range of historical values that it's seen. And so that could be an issue with time series forecasting. You might be trending up or down, and you might have to actually extrapolate beyond the range of past values. And so the whole point of using that kind of algorithm is to make it relatively safe, so that you're not really in danger of having to forecast outside of whatever range that the model's seen. So here you're kind of looking for just kind of this flat trend across the entire training data set with potentially lots of patterns still left. We're going to leave whatever patterns left to the tree-based algo to figure out. And so for the second model, basically we've got this detrended data. So that's the target for the tree-based ensemble. And we're going to use all sorts of features that we can extract from the calendar or the date. And so like day of the week, day of the month, holidays, whatever else we think is important. For this particular approach, I used a HIST gradient boosting regressor from scikit-learn. This is a light GBM implementation in Python. And I use pretty much all the defaults except I up the iterations and tree depth a little bit. Obviously, with any of these kinds of algorithms, you can play around with the tuning parameters or even go through, more formal parameter tuning process to try to figure out what the best combinations are. The nice thing about tree-based ensembles, in my experience, is that they're fairly robust to, using default or close to default parameter values. And so here's what those models trained and then forecast. I added in the dotted line there as the trend. So the kind of the thick dotted line is the fitted trend and then the forecasted trend. And then the actuals past the green, past the red, are what the tree-based algo figured out on top of the trend forecast. And so I'll kind of go back to that split 1 versus split 2. You see the trend, thought it was going to be flat. It ended up going up quite a bit. But if you kind of go back and look at what data we had to train on those 4 years prior to that one, it was fairly flat. So it wasn't really that unreasonable to think that it would continue to be flat. It ended up increasing. So that forecast ended up not being very quite as accurate. One thing that you can do too with this is you can try to figure out, well, is my model performing poor or not so well because of the forecast or the trend or because of the cyclic piece? You can kind of break those down and sort of get a feel for which component is contributing more or less to the accuracy of the model. So now something to compare to, we'll go back to this Auto-ARIMA procedure. It's implemented in Python using PMD ARIMA library, and it's very similar to this forecast package in R. If you use R, Rob Heineman's package on forecasting is really, really handy. He has a function in there called auto.arima that's basically the same thing. So this time around, we're going to use something called Sarima Max, which is ARIMA with the seasonal feature turned on. So that's where the S comes from. And then the X at the end is for exogenous regressors, or basically external regressors. We're going to use the calendar features for these. One note on this, I'm certainly not an ARIMA expert, but I've read and heard that it can be useful for this particular implementation to use Fourier transforms instead of the raw calendar features like integer values. It's essentially like a sine, cosine, or equivalent type of a exogenous regressor. I didn't do that in the simulated data set, but you could certainly play around with that and try that. Another thing that I did differently this time around is there's a parameter in Auto-ARIMA called max iterations, and the default's 50. And so I brought that down to 10 just to kind of make it go a little bit faster for troubleshooting purposes. So here's what the Auto-ARIMA procedure spit out with basically a Sarima X model. And you can see it did really well at the day of the week stuff. You can kind of see where it picked up some of the holiday effects, but the general kind of day of the year patterns aren't really there. It's fairly flat. You can see the trends a little bit where it's picking up some of those. It also didn't do a very good job between split 1 when it was on split 1 trying to figure out that trend going up. Obviously, in the simulated data set, we just randomly made that, so it wasn't like it had any real clue that that was going to happen. But it also kind of just thought that trend was going to be flat and ended up going up a little bit more. So it was kind of interesting to compare those a little bit. And so this is what I've kind of been talking about. This is that particular split where that actuals was kind of coming out of a fairly flat amount, and then the second half of that year, the trend kind of went up. Both the ARIMA model and the tree-based model didn't see that trend coming, and they both kind of suffered on this particular split in terms of forecast accuracy. And obviously, that's a challenge anytime you're doing long-term forecasting with how far is that trend gonna, the further out you go, it may not always behave or do the things that you think it's gonna do.
So the top is actual, then ARIMA, and then bottom is tree. And tree prediction looks like much better than ARIMA in the middle, right?
Yeah, I mean, it definitely captured a little bit more realistic looking day of the week and day of the month. I mean, the ARIMA pretty much didn't even figure out what day of the month effects were going on. You can kind of see the day of the month effect in the tree one. But yeah, in general, the tree got a little bit more. It's interesting though. I think the next slide is where all of them are at. There was that one split where the trend kind of dove a little bit for the tree-based algo, and it actually went up. That particular split kind of made it so that the tree-based algo, when you averaged across all the splits, was slightly worse because that one split was a little bit worse. But in general, if you compare the accuracy of these two methods, they're basically identical. And then the big difference, the big benefit in my mind, is with the Auto-ARIMA procedure, you're looking at, on my machine anyway, a minute, 2 minutes, sometimes 3 minutes per split. And so if you're just building one model, that's probably fine. But if you're building dozens or maybe even hundreds of individual time series forecasts, and each one takes 2 or 3 minutes to train, that can be kind of a constraint on your whole process. The real big benefit of this XGBoost tree-based approach is you can literally build these and they can train in a couple seconds. And so if you need to train dozens or hundreds of models, it really becomes scalable with that amount of time to train. Okay, so any questions on the simulated stuff before we kick over to the Kaggle data set? The Kaggle data set's a little bit more interesting, but just want to pause there for a sec. So moving on to this Kaggle data set, I've got the link to it here. It's a daily website visitors to a particular website called statforecasting.com, and you can kind of see a little bit of the description there. It's got a real strong day of the week pattern, and it also kind of follows this, they say, the academic calendar. I assume it's because it has a lot of people looking at it during the school year versus not in the summer. You can kind of see, I'm assuming this is sort of like the holiday break that universities take right at the end of the year. Every year the visits kind of tumble right at the end of the year, and then maybe this is summertime, but you can kind of see there's this pretty clear pattern throughout the course of the year, as well as throughout the course of the week. And then it's got not much of a trend, but a little bit of a trend throughout it. So this kind of data set is very similar in terms of characteristics to the type of data that I've been working with our call center. So I thought it was a good one to walk through as an example. So revisiting that whole procedure this time, for those of you who are visually a little bit more stronger, kind of showing what we're doing with some visuals. So the blue boxes are all applied to the training split if you're doing backcasting, or if you're making legit forecasts, it's all your actual historical data. And then the orangish boxes are your testing split, i.e. the future forecasts or future predictions. So the first thing we do is we decompose the time series using STL. Then we fit an auto-reg model to that trend. We also use the trend to extract the residuals of the trend model, if you will, and feed that to our XGBoost or tree-based model. Then we make two separate forecasts, one for the trend, kind of the long-term forecast using the trend, and then the tree-based model makes a prediction on all the cyclic patterns and all the other, basically the residual. And then our overall forecast is adding those two together. So here's, again, I use 4 splits, 365 days in the forecast horizon. So here's the trend component. So you can kind of see how the trend stays mostly flat throughout it, but for some of them, it was kind of pointing up or down a little bit. again, you could play around with the parameters here. You could even fit the trend to, get much more wiggly and try to explain a lot more of this kind of intra-year pattern if you wanted to. So you really have a lot of flexibility with how you address the trend. I tend to try to do the long-term trend approach a little bit more and let the tree-based algo handle all the other stuff. So here's the detrended. Again, we're trying to look for fairly flat data that's sort of centered around 0, so that the tree-based model is pretty safe in terms of making its prediction within the bounds of historical data. So on the left here, we've got our tree-based algo predictions with the dotted lines as the trends. So for all 4 splits. And on the right, we've got the Auto-ARIMA procedure using the same parameters I talked about for the simulated data set. It did a little bit better in terms of kind of the day of the week stuff. It really picked up. But the Auto-ARIMA model, we didn't explicitly give any features for this end of year stuff other than the day of the year, which the tree-based algo figured out pretty well. It almost looks exactly like what happens when you actually got to that point, whereas the ARIMA model didn't really capture that. It kind of smoothed over it. So overall, on this Kaggle data set, the tree-based algo was quite a bit better in terms of the accuracy, a measurable difference than the model produced by Auto-ARIMA. And then again, in terms of training time, it was magnitudes difference, a couple of seconds per split on the trend plus tree model, and then a couple of minutes per split on the ARIMA procedure. So just a couple of things to kind of note, and then we'll have some questions, comments. A couple other tools that I've used for this kind of stuff. I have been using Azure a lot, as I mentioned earlier, and they have the AutoML functionality. You can actually give it time series data and specify to make time series forecasts. You can do it with a no code option, which takes about 3 minutes to upload the data set and kick it off. Or you can write a script using the Python SDK to kick off an AutoML run. I've also been using, if you're an R user, been playing around a little bit with this package called Model Time, which is kind of a wrapper around a lot of common forecasting packages in R. Kind of has a tidyverse theme to it. So if you like tidyverse stuff, then that'll be a good one to use for time series. And then a couple other ones that are pretty prevalent out there that I want to play with. Profit and Neural Profit from Facebook. Profit you can get both on Python and R. And I haven't used Neural Profit before, but it's supposedly a lot faster than Profit is. And kind of want to play around with those a little bit, see how it works with some of this data. But that was it. Anyway, if there are any questions or comments, I'll go ahead and open it up.
I guess I have a quick question. So you mentioned how there's that part where you could just kind of import the data set and just have it do everything on its own. Have you used that often?
Yeah, the AutoML.
Yeah.
Yeah. So actually was just playing around with that Kaggle data set now. What I've done with it is I've found it's really handy at the beginning stages when you maybe are exploring, hey, is this something that we should use? Kind of working with the business side of things, like, hey, can we, forecast this particular problem? And, this is how far out we want to forecast, because it's not a lot of effort to get the data set up and just let it go. And you can pretty much get it up and running in a handful of minutes. And so I've used that as kind of an initial check to say, well, what kind of performance could we expect for this particular data set?
Hold on. It shows it's running almost 4 hours.
Yeah.
Yeah, it's
Wow.
been running for a while. But even if it's still running, you can still access results throughout it. So this is partial results, if you will. But these are all the algorithms it's tried. It's tried 49 different models so far, and you can sort by, in this case, normalized means root squared error. So you can get, smaller values of the best ones. And typically with the data sets I've been working with, it's always random forest or some kind of gradient boosted machine One of these down here, profit models in here, so it's fairly competitive, but most of these tree-based ones are slightly better. And so the other nice thing about these is, I'll do something like this AutoML, come in here and say, okay, I'll do light GBM. What kind of parameters should I start with? Should I use the defaults? Maybe I should try some, this one tried a square root for the max features. This one tried 0.7 for the max features. So it kind of gives me a handle on what parameters maybe I should start with, as opposed to other ones where maybe I can just use the defaults. So I've used that for time series, just to kind of initialize the development, if you will. I haven't ever used AutoML to deploy the model for time series, because in my experience, you typically always want to, whenever you're going to make a forecast, get as much historical data, retrain the model, and make the new forecast, as opposed to having a static model that you feed new prediction values to. So kind of having a full sort of update the data, retrain the model, make the forecast process is sort of the way that I would lean, and deploying the model isn't really useful for that.
Got it. Thanks. Small follow-up. Is it more expensive to run that one, or?
Yeah, these ones, the cost is whatever your compute is.
Right.
And so I think on mine, the compute cluster, it's like $0.25 an hour or something, or 20 cents an hour. So, this runs kind of cost a cup of coffee. So it's not that bad.
That's not horrible.
No. If you had much larger data sets, it might take longer. You can also add, I haven't played with this before, but you can add some guardrails like early stopping criterion. I think you can add like a max runtime. Like, let's say you said, hey, I don't want this thing to run more than 2 hours, and just whatever you have after 2 hours, shut it down. And I'll take what you give me. The other nice thing about this is you can kind of set it off and run it behind the scenes, and it just is going, and you don't have to really worry about it taking up resources on your local machine. You can kind of work on 2 things at once, which is kind of handy too. But yeah, the cost so far hasn't been super crazy, but then again, I've been dealing with fairly small data sets, 5 to 6 years of daily data is not very big. So if you had much larger data sets, it might start to be a little bit more of a consideration.
Okay. I guess this is the end. Brett, this was really, really good presentation, and very interesting results, and very useful results, because people can have good quality predictions which are running like 100 times faster.
Definitely been helpful. My business case has been, basically about 25 different models that I build, and the whole thing runs in about 2 minutes. So it's pretty handy.
Okay, thank you very much. I'll stop the recording.